This conference will now be recorded.
Good morning, students. We are discussing the Unit 3, Part 1 in Hydraulic Engineering. In this Part 1, already we discussed the impact of water jet on stationary metal plates. So far, in Part 1 of Unit 3, we discussed the impact of water jet on the stationary metal plate. In that, we discussed the flat metal plate. In that flat metal plate, first we discuss the water jet is horizontal and the flat metal plate is vertical. Stationary flat metal plate is vertical. That is the first condition. So in that, the flat metal plate is perpendicular to direction of water flow. Then we discuss the impact of water jet on the stationary inclined flat metal plate. We discussed that in the previous classes. The striking of horizontal water jet on the stationary inclined flat metal plate. After that, we started the curved metal plates. In that curved metal plate, again we have three conditions. The first condition, the horizontal water jet strikes the symmetrical stationary curved metal plate at the center. That is the first condition. The second condition, the water jet strikes the symmetrical curved metal plate in the tangential direction. Then the last condition is the water jet strikes the stationary unsymmetrical curved plate in the tangential direction. So far, in part 1 of unit 3, we discussed these impacts of water jet on the stationary metal plate. In all these conditions, by using Newton's second law of motion, we prepare the equations for the x-axis force Fx and y-axis force Fy. So far, we discussed that impact of water jet on stationary metal plate. In that, we discussed the equations for the forces exerted by water jet in those metal plates. While preparing that equations, we apply the Newton's second law of motion. Number of times we discussed in the previous classes. According to Newton's second law of motion, the force is equal to rate of change of linear momentum of water jet in the direction of force. By using that Newton's second law of motion, we discuss the equations for the force exerted by water jet on the metal plate. Then we have in this unit 1, the next topic, the force exerted by water jet on a hinged metal plate. So please go through the title on the screen. The force exerted by water jet on a hinged metal plate. In this discussion, we consider the metal plate is a flat metal plate. Here we consider the metal plate is a flat metal plate, and we are going to discuss when that metal plate, hinged metal plate, the metal plate is having the hinge at the top. When the water jet strikes the hinged flat metal plate, there is a deflection in that metal plate. If the metal plate is vertical, the hinged metal plate is vertical. If the water jet strikes that hinged metal plate, vertical metal plate, the metal plate undergoes to deflection because the water jet applies the force on the metal plate. Here we assume the water jet is horizontal. The hinged metal plate is stationary vertical metal plate. Since it is hinged metal plate, when the water jet strikes the metal plate, there is a deflection in that metal plate because of this hinge arrangement. We are going to discuss what is the deflection If the deflection is theta, initially the metal plate is vertical. But when the water jet strikes the metal plate, there is a deflection in the metal plate. With respect to vertical, the metal plate undergoes to deflection. We are going to discuss in this topic what is the angle of deflection of the metal plate, hinged metal plate, when the water jet strikes that metal plate. That is the topic in the today's class. We are going to discuss in part 1 of unit 3. Now coming to this diagram. Observe this diagram for this topic. Check this diagram please. So in the diagram, we have the horizontal water jet. The water jet coming out from the nozzle with a velocity v meter per second. The water jet strikes the vertical flat metal plate, stationary metal plate. This metal plate is the vertical stationary metal plate, but here the metal plate is hinged metal plate. There is a hinge provided at the top of the metal plate. Now, when the water jet strikes the metal plate, the metal plate undergoes to deflection because the water jet applies the force on the metal plate. Because of that force, there is a deflection in the metal plate. So this is the deflected condition of the metal plate. So here, initially the metal plate is vertical. The hinged metal plate is vertical, but the metal plate is subjected to the impact of horizontal water jet. We know that when the water jet strikes the metal plate, the water jet applies the force, horizontal force on the metal plate. Please remember, in the first condition, we discussed this impact of water jet on the stationary vertical metal plate. If the metal plate is a stationary vertical flat metal plate, we discuss this impact of water jet on the metal plate and we prepare the equation for horizontal force Fx acting on the metal plate due to this water jet impact. Please remember, in that condition 1, we prepare the equation of Fx. Fx is equal to rho a into v square. By using Newton's second law, we prepare the equation of force exerted by water jet on the stationary flat vertical metal plate. Fx is equal to rho a v square. Rho is the density of water, a is the area of the water jet, v is the velocity of water jet. So here also the metal plate is stationary. It is a flat metal plate, vertical. So when the water jet strikes the metal plate, the water jet applies the force on the metal plate, that is F. Because of that force, there is a deflection in the metal plate. Due to this force F, let the metal plate subjected to the deflection by an angle theta. Initially the plate is vertical, but when the water jet applies the force on the metal plate, there is a deflection in the metal plate. That angle is theta. We are going to discuss what is the equation for this angle theta. What is the equation for this angle of deflection theta when the water jet, horizontal water jet, strikes the vertical metal plate having the hinge at the top? So please everyone check the diagram carefully. Here the water jet is horizontal, the metal plate is vertical. The water jet strikes the metal plate at the center. This is point C, center of the metal plate. Then after the deflection, this is the deflected condition of the metal plate. Because of the force exerted by the water jet on the metal plate, due to this force F, the metal plate subjected to deflection. After the deflection, the water jet is acting on the metal plate at point B. So check that carefully. Once this plate subjected to deflection, the point C is moving up to this position, whereas the water jet is horizontal. So after the deflection of the metal plate, the water jet strikes the metal plate at point B on the metal plate, whereas the weight of metal plate is W. Take the weight of the metal plate is W. Weight of the metal plate always acting from the center of the metal plate. C is the center of the metal plate. We know that this impact is the impact of horizontal water jet on the stationary vertical flat metal plate. We discussed this in the condition 1. In part 1, first we discuss this particular situation. That is condition 1. The impact of horizontal water jets on the stationary vertical flat plate. This is the diagram. The water jet is horizontal, moving with velocity v. The water jet strikes the metal plate. The metal plate is stationary, vertical, flat metal plate. The metal plate is perpendicular to direction of water jet. Then this water jet applies the force Fx on the metal plate. We discussed that derivation of force Fx by using Newton's second law of motion. Fx is equal to rho A into V square. Rho is the density of water. A is the area of the water jet. V is the velocity of water jet. So we know this force magnitude, the force exerted by horizontal force, the force exerted by the water jet on the metal plate is given by rho A V square. Now check this force. The force is acting on the metal plate at point B. The force of the water jet is acting on the metal plate at point B. Now on this deflected metal plate, resolve this force F acting at point B into two components. On this deflected metal plate, resolve this force F exerted by water jet on the metal plate. That force F is equal to rho A into V square. After the deflection, the force F is acting on the metal plate at point B. Now at point B, resolve this force F into two components. One component perpendicular to the surface of the metal plate in this direction. Resolve this force F acting on the metal plate into two components. One component perpendicular to surface of the metal plate along this normal direction. Take that component as Fn. Next component is along the axis of the metal plate, that is tangential component. So at point B, after the deflection of this metal plate, we know that when the water jet strikes the metal plate, since the metal plate is a hinged metal plate, there is a hinge at the top of the metal plate. Since the metal plate is a hinged metal plate, when the water jet strikes the metal plate undergoes to deflection. Theta is called angle of deflection. The angle made by the deflected metal plate with vertical. Initially the metal plate is vertical. Now the force applied by the water jet on the metal plate is acting at point B, not on the point C, because it is the deflected position. In the deflected condition, the force is horizontal. It is acting on the metal plate at point B. Now at point B, resolve this force F into two components. One component in the normal direction. This is normal to the metal plate at point B. This line is normal to metal plate at point B. This normal line with horizontal making the angle theta. With respect to horizontal, this normal line makes the angle theta, because the axis of the metal plate with vertical making the angle theta, the normal to the axis of the metal plate with horizontal makes the angle theta. So resolve this force F acting on the metal plate at point B into normal component and the tangential component. The normal component Fn is F cos theta. The tangential component Ft is F sin theta. So resolve the force F. What is this force F? It is the force exerted by the water jet on the metal plate because of impact. We know already the equation of this force F, rho A V square. In the first class, we discussed that condition. the impact of horizontal water jet on the stationary vertical flat metal plate. In that discussion, we prepare the equation of force Fx, horizontal force, rho a v square. Here also, the same force is acting on the metal plate. Because the water jet is horizontal, the metal plate is stationary, vertical, flat metal plate. The equation of this horizontal force F is equal to rho a v square. We resolving this force F at point B into two components. One is normal component Fn, next one is the tangential component Ft. Normal component Fn is equal to F cos theta. What is the force F? Rho a v square into cos theta. Rho a v square force F. So the normal component Fn acting at point B perpendicular to the metal plate is Fn F cos theta rho a v square into cos theta. Then this tangential component, that is the component in the axis of the metal plate Ft. Ft is equal to F sin theta, that is equal to rho a v square into sin theta. So we are discussing the impact of horizontal water jet on the hinged vertical flat metal plate. That is the condition. In the today's class, we are discussing the impact of horizontal water jet on the vertical hinged stationary flat metal plate. Because of the impact of the water jet on the metal plate, due to this hinge, the metal plate subjected to deflection. After the deflection, let the metal plate makes an angle theta with vertical. We are going to find out the equation for this theta. What is this angle of deflection of the metal plate, hinged metal plate, due to the impact of the water jet? Now, after the impact, the force exerted by the water jet on the metal plate is acting at point B horizontally. F is the force. The equation of force F is rho a into v square. At point B, resolve the force F into two components. One is normal component Fn perpendicular to the metal plate surface, that is this normal component Fn perpendicular to the surface of the metal plate. Next one is the tangential component Ft along the metal plate. This Ft is along the axis of the metal plate. The normal component Fn is equal to F cos theta. Tangential component Ft is equal to F sin theta. Now check this metal plate after the deflection. After the deflection, the metal plate is subjected to totally three forces. After the deflection, the metal plate is subjected to three forces. First force is the weight of the metal plate W passing through point C. C is the center of the metal plate. Three forces are acting on the metal plate after the deflection. One is the weight of the metal plate W. Next one is the normal force Fn passing through point B. Second force, normal force Fn passing through point B. Third one is the force Ft on the axis of the metal plate. Three forces are acting on the metal plate after the deflection. First force is the weight of the metal plate W passing through this point C. Next one is normal force Fn passing through point B in the perpendicular direction. Third force is Ft along the axis of the metal plate. Three forces are acting on the metal plate after the deflection. We are going to prepare the equation for this angle theta. To prepare the equation for this angle theta, find out the moments of, please listen this carefully. To prepare the equation for this angle theta, find out the moments of these three forces. What are those three forces? W, Fn and Ft. Find out the moments of these three forces acting on the metal plate about this hinge O. To find out, to prepare the equation for the angle theta, that is called angle of deflection of the hinged vertical metal plate. To find out the equation for that angle theta, first find out the moments of three forces W, Fn and Ft acting on the metal plate after the deflection. First take the force Ft. The force Ft is acting on the axis of the metal plate. The force Ft line of action passing through point O. We know that moment is equal to force into perpendicular distance. The force Ft passing through point O, that is the hinge, passing through the point O, that is hinge. Since the force Ft is passing through point O, that is the hinge, the moment of this force Ft about the hinge is 0. There is no perpendicular distance for the force Ft, because the force Ft is passing through the hinge point O. So the perpendicular distance is 0. So the moment of force Ft about point O is 0. Then the second force is W. This is the line of action of force W, vertical line of action from point O, that is hinge, to this force W. OD is the perpendicular distance. So check the second force, the weight of the metal plate W. The weight of the metal plate is vertically downwards. This is the weight of the metal plate W. Then from this hinge point O to this force W, the perpendicular distance is OD. Find out this length OD to calculate the moment of the force W about the hinge O. Moment of force W about the hinge O is force W into the perpendicular distance OD, because to this force W from this hinge point O, the perpendicular distance is OD. So the moment of force W about this point O is force W into perpendicular distance is OD. So calculate first the length of this perpendicular distance OD. To find out that length OD in the diagram, take the right angle triangle OCD. This is the right angle triangle. Take the right angle triangle OCD in the diagram. Coming to this diagram carefully, before deflection from point O to point C, take the length as X. X is the length from point O to the point C. C is the midpoint of the metal plate. O is the hinge point. Let the distance OC is equal to X. After the deflection also, the length OC is X. Length OC is X with vertical, the axis of the metal plate making the angle theta. With vertical, after the deflection, the axis of the metal plate is making the angle theta. So with the horizontal, the axis of the metal plate makes the angle of 90 degrees minus theta. With vertical, the deflected metal plate making the angle theta. So with horizontal, the metal plate making an angle of 90 minus theta. Take this right angle triangle OCD. In that OCD right angle triangle, the length OX, OC is X. The length of OC is X. We require this length OD. Since we require the length OD, take cos 90 minus theta in the right angle triangle OCD. Cos 90 minus theta is equal to adjacent side is OD, hypotenuse is OC. So in the right angle triangle OCD, cos 90 minus theta is equal to OD divided by OC. OC length is X. So OD is equal to OC into cos 90 minus theta. Cos 90 minus theta is sin theta. So sin theta is equal to OD divided by OC. But OC is equal to X. So cos 90 minus theta is equal to sin theta, that is equal to OD divided by X. So the length OD is equal to X into sin theta. So in that diagram, the length of OD in the right angle triangle OCD is X into sin theta. We have this second force W. This is the second force W, vertical. From point O, hinge point O to this force W, OD is the perpendicular distance. Just now we calculate this length OD, x sine theta. So the moment of force W, the moment of this force W about the point O, hinge point. The moment of force W about the hinge point O is W into the perpendicular distance OD. What is that length OD? X into sine theta. So the moment of force W about the hinge point O is equal to W into OD, that is equal to W into x sine theta. About this hinge point O, the force W produces the clockwise moment. About the hinge point O, the moment of force W is clockwise moment. We are determining the angle theta. We are going to discuss the equation for this angle theta. To prepare the equation for this angle theta, we are calculating the moment of three forces acting on the plate after the deflection. After the deflection, the metal plate subjected to three forces: force Ft, force W, force Fn. The force Ft passing through point O, hinge point O. So the moment of force Ft about the hinge point O is 0. Then the moment of force W about the hinge point O is W into the length OD. We know that the length OD is equal to x sine theta. So the moment of force W about the hinge point O, W into x sine theta, that moment is in the clockwise direction. Then the third force is Fn, normal force. This is the line of action of normal force. From point O to that normal force, the perpendicular distance is OB. OB is the perpendicular distance of this normal force from this point O. From the hinge point O to this normal force Fn, the perpendicular distance is OB. So find out this length OB first. To find out this length OB, take the right angle triangle OBC. Here we have the right angle triangle OBC. In that right angle triangle OBC, with respect to this angle theta, take the right angle triangle OBC. In that OBC right angle triangle, with respect to the angle theta, sin theta is equal to, or cos theta is equal to. So take the right angle triangle OBC, because we require this length OB. OB is the perpendicular distance from point O to this line of action of force Fn. To find out the value of length OB, take the right angle triangle OBC. In that right angle triangle, we have the angle theta at point O. So take cos theta in that triangle. Cos theta is equal to, adjacent side is OC. In that OBC right angle triangle, with respect to theta, OC is the adjacent side, OB is the hypotenuse. So cos theta is equal to OC divided by OB. But OC is equal to x. So in that right angle triangle OBC, cos theta is equal to OC divided by OB, but OC is x. So cos theta is equal to x divided by OB. So the length OB is equal to x divided by cos theta. So from the right angle triangle OBC, we calculate this length OB, x by cos theta. Then the moment of force Fn about point O. The moment of this force Fn about point O is Fn into the length OB, because it is the perpendicular distance. So Fn into length OB is the moment of this force Fn about point O. That moment of force Fn is in the anti-clockwise direction. So after the deflection, this metal plate having the hinge at top, the metal plate after the deflection subjected to the moment due to the weight of the metal plate, that is W into OD in the clockwise direction. Then also the moment due to force Fn, that is Fn into the perpendicular distance OB in the anti-clockwise direction. So after the deflection, the hinge plate subjected to two types of moments. Clockwise moment due to weight W, anti-clockwise moment due to force Fn. Now coming to this calculation of angle theta. So far I explained the concept theory in this impact of water jet on the hinged metal plate. So in this condition, in this discussion, we consider theta is the angle of deflection of the metal plate. W is the weight of the metal plate. X is the distance from the hinge point O to the center of the metal plate C. V is the velocity of the water jet, and D is the diameter of water jet. So the area of the water jet is pi by 4 into d square. You know that when the water jet hits the metal plate, the water jet applies the force F, horizontal force on the metal plate. Since the metal plate is a vertical flat metal plate, in the rest condition initially, the equation of force F is rho A into V square. We discussed this equation in the first condition. The impact of horizontal water jet on the stationary flat vertical metal plate. We discussed that equation. So we are using that equation in this condition. The horizontal force F is equal to rho A into V square. After the deflection, the water jet hits the metal plate at point B. So at point B, we resolve the force F into two components. So please go through the slides carefully. After the deflection, the water jet strikes the metal plate at point B. At point B, we resolve the force F into two components, the normal component Fn, the tangential component Ft. Fn is equal to F cos theta. But what is that force F? Rho A V square. So Fn is equal to rho A V square into cos theta. Ft is equal to F sin theta. That is rho A V square into sin theta. So at point B, we resolve that force F acting on the metal plate into two components. Normal component Fn, tangential component Ft. Fn is equal to F cos theta, rho A V square into cos theta. Ft is equal to F sin theta, rho A V square into sin theta. Then we calculate the moment of forces. Three forces are acting on the metal plate. Force Ft, force W, force Fn. Force Ft passing through the hinge point O. The force Ft passing through hinge point O. So the moment of force Ft about hinge point O is 0. Then the second force is the weight W of the plate. The moment of weight W of the plate about hinge point O is W into OD. This is the moment of the weight W of the plate about the hinge point O. W is the force, OD is the perpendicular distance. So the moment of the weight of the plate about the hinge point O, W into OD. To calculate this length OD, we consider the right angle triangle OCD. In the right angle triangle OCD, the angle is 90 degrees minus theta with horizontal. So cos 90 minus theta in the right angle triangle OCD. Cos 90 minus theta is equal to OD divided by OC. The length OC is equal to X. Cos 90 minus theta is equal to sin theta. So sin theta is equal to OD by X. So the length OD is equal to X sin theta. Then find out the moment of the weight of the plate above the hinge point O. That is equal to W into OD X sin theta, because the length OD is X sin theta. So W into X sin theta, this is the moment of the weight of the plate about the hinge point O. That moment is in the clockwise direction. After that, we consider the force Fn, third force. The force Fn is acting perpendicular to the metal plate at point B. Then the moment of force Fn about the hinge point O is Fn into OB. From the hinge point O up to that force Fn, the perpendicular distance is OB. So the moment of force Fn about the hinge point O is Fn into OB. To calculate the length OB, we consider the right angle triangle OBC. In the right angle triangle OBC, at point O, angle is theta. So cos theta is equal to adjacent side is OC, hypotenuse is OB. OC is equal to X. So cos theta is equal to X by OB. So the length OB is equal to X by cos theta. You know that force Fn is equal to rho A V square into cos theta. We know this normal force Fn rho A V square into cos theta into the perpendicular distance is OB, X by cos theta. X will cancel. So this cos theta will cancel on the right side. So the moment of the normal force Fn about the hinge point O is rho A V square into X. That moment is anti-clockwise. So after the deflection of the metal plate, two moments are acting on the metal plate about the hinge point O. One is the moment of the weight of the metal plate Wx sin theta. Next one is the moment of the force Fn about hinge point O, rho A V square into X. You know that the algebraic sum of the moments about the hinge is always equal to 0. That is the condition of hinge. Already you might have studied in the strength of materials. If the beam is having the hinge support, since the hinge allows the rotation, the moment of all forces acting on the beam about that hinge is always 0. So in this discussion, the hinge on the metal plate subjected to two moments. One is the moment of the weight of the plate Mw clockwise. Clockwise moment is positive. Next, the moment of the force Fn, that is anti-clockwise. We calculated these two moments, the moment of the weight and also the moment of Fn. We calculate these two moments about the hinge point O. We know that algebraic sum of the moment of forces about the hinge is 0. Since in this condition, the metal plate contains the hinge at the top, the algebraic sum of these two moments Mw and Mfn, algebraic sum of these two moments about the hinge is 0. By using that condition, you will get in this hinged metal plate the required condition about the hinge. Algebraic sum of the moments is 0. How many moments are acting on the hinge? Two moments. One is the moment of the weight of the plate Mw, clockwise, positive moment. Next one is the moment of the force Fn, anti-clockwise. So about the hinge support on the metal plate, algebraic sum of the moments is 0. Sigma m naught. O is the hinge support. Since there is a hinge support on the vertical metal plate at the top, algebraic sum of the moments of forces about the hinge support is 0. So sigma m naught is equal to Mw minus Mfn equal to 0. We know that Mw, the moment of weight of the plate Mw is equal to W into x sin theta. The moment of Mfn is rho A V square into x equal to 0. We discuss the moment of the weight of the plate about the hinge point O, W into x sin theta. We discuss the moment of force Fn about the hinge point O. Mfn is equal to rho A V square into x equal to 0. Bring this second term to the right side. So this equation becomes as Wx sin theta is equal to rho A V square into x. Cancel the x on both sides. So from this equation, you will get sin theta is equal to rho A V square by W. This is the equation to find out the deflection of the hinged vertical metal plate, flat metal plate, due to the impact of horizontal water jet. So in this condition, we have the hinged vertical flat metal plate. The water jet is horizontal. That water jet strikes the metal plate at the center. Because of that impact, there is a deflection in the vertical plate. The vertical plate subjected to the deflection theta due to the impact of water jet on the metal plate. We consider the forces acting on the metal plate, the force W, the force Fn, and force Ft. We found the moments of these three forces about the hinge point O. The moment of force Ft is 0. The moment of weight W, Mw is equal to W into x sin theta. The moment of force Fn, Mfn is equal to rho a v square into x. Since we calculate the moments about the hinge, always about the hinge, algebraic sum of moments is 0. So about that hinge, sigma m naught is equal to Mw minus Mfn 0. From this Mw Wx sin theta, Mfn rho a v square into x equal to 0. By simplifying this equation, we got finally sin theta is equal to rho a v square by W. On the right hand side, rho is the density of water, A is the cross sectional area of water jet, V is the velocity of water jet, and W is the weight of the metal plate. By using this equation, we can find out this angle theta. Theta is called the deflected angle, angle of deflection of the hinged vertical metal plate. So this is the impact of water jet on the hinged vertical flat metal plate. Dear students, if anybody is having doubt about this derivation of sin theta, you please discuss with me. If you have doubt about this derivation of sin theta in this hinged vertical flat metal plate, you please discuss with me. Any doubts in this impact of horizontal water jet on the hinged vertical metal plate? If you have doubts about this, you please discuss with me. Okay, students, we started this. Please, everyone listen carefully. Still only 32 members are there in the class. Your class strength is almost 60. What about the remaining students? Only 32 members are there in the class. My dear second year, second semester students, number of times I informed you, this hydraulic engineering is the toughest subject. I am requesting you at least to join the class regularly. You cannot understand these concepts by your own or by listening my YouTube videos. Watching my YouTube videos, you cannot understand these concepts. If you attend the class, if you are unable to understand, I will explain this number of times. Why you people are absent for the class? What you are doing at home? Only regulars, only few students daily. At present, I have only 32 students in the class. Every day, these students are only attending the class. Remaining are irregular. Definitely tomorrow or day after tomorrow, they will face the problem in this subject. This is the most toughest subject. Please inform to your friends to join the class regularly, at least for my hour. At least for my hour. I am requesting you, my dear students. Please inform to your friends to join the class regularly. You cannot understand by your own or by watching my YouTube videos. Anyway, I am uploading all these videos in the Adisankara media. You can go through those videos. But if you got the doubt while watching those videos, who will explain those doubts? Okay, my dear students, those who are there in the class, thanks to one and all. Dear students, so far we discuss the impact of water jet on the stationary metal plate. So please follow this carefully. So far we discussed the impact of water jet on the stationary metal plate. We discussed different conditions: the vertical flat metal plate, the inclined flat metal plate, the symmetrical curved plate, the unsymmetrical curved plate. We discuss number of conditions in the stationary condition. We discuss all those cases in the stationary condition. Then the next one is sometimes the metal plate is also in moving condition. So please carefully understand this concept. So far we discuss the rest condition of metal plate. Only the water jet is moving. Only the water jet is in motion, whereas the metal plate is in rest condition. We discuss number of cases in this part 1. The vertical flat metal plate stationary, the inclined flat metal plate stationary, symmetrical curved plates, unsymmetrical curved plates. In all those cases, only the water jet is moving and the metal plate is in rest condition. By using Newton's second law of motion, in that rest condition, we prepare the equations for the forces Fx and Fy. Now we are going to the next part in the unit 3 part 1, that is the metal plate is also in the moving condition. So please check this carefully, observe this carefully. Not only the water jet, we are going to consider the metal plate is also in moving condition. Again, in the moving condition, we have all the previous cases. We consider the vertical flat metal plate in the moving condition. We consider the inclined flat metal plate in the moving condition. We consider the symmetrical curved plate in the moving condition. We consider the unsymmetrical moving plate in the unsymmetrical curved plate in the moving condition. Now, when the metal plate is also in the moving condition, how can we apply the Newton's second law of motion to find out the forces exerted by the water jet on the moving plates? So in this part 1 of unit 3, we are going to consider the motion of the metal plate also. This is the practical condition. Always the metal plate is not in the rest condition. Sometimes the metal plate is also in the moving condition. When the metal plate is in moving condition, what is the equation for the force exerted by the water jet on that moving plate? So please coming to that next topic in the part 1, that is the impact of water jet on the moving metal plate. So please everyone, look this PPT on your cell phones. Please give me the response. Can you see this PPT on the cell phones? Force exerted by water jet on a moving plate. Is it visible on the cell phones? Please give me the response. Can you see this on the cell phones? Force exerted by water jet on a moving plate. Thank you. So here we are going to the next condition in the part 1. So far we discussed only the stationary metal plate, but sometimes the metal plate is also in moving condition. When the metal plate is in moving condition, how to calculate the force exerted by the water jet on the moving metal plate? In that moving condition, again we have some subconditions. When the metal plate is in moving condition, we have the same subconditions. The first one, the following cases of moving plate will be considered. The first one, the metal plate is flat vertical metal plate moving in the direction of water jet. So check that first one. The metal plate is flat vertical metal plate. The metal plate is not stationary. The metal plate is moving in the direction of the water jet. Second case, the metal plate is flat inclined metal plate. it is moving in the direction of the water jet. Third condition, the metal plate is curved metal plate. The metal plate is curved metal plate. It is moving in the direction of water jet or horizontally. Like that, in the moving metal plates, we have these conditions. The first condition, the moving metal plate is flat vertical metal plate. It is moving in the direction of water jet. Second condition, the moving metal plate is a flat inclined metal plate. It is moving in the direction of water jet. Third condition, the moving metal plate is a curved metal plate. It is either moving horizontally or moving in the direction of water jet. For all these conditions in the moving metal plate, we are going to discuss the equations of forces exerted by the water jet on the metal plate. Now coming to the basics of this moving condition. To understand this moving condition, I am going to discuss with you one fundamental concept to understand the moving condition of the metal plate. So please everyone look this PPT on your cell phones. Look this PPT. When the metal plate is in moving condition, we must consider one important concept, the relative velocity. When the metal plate is in moving condition, we must consider the physical phenomena of relative velocity. I hope in the lower classes you might have studied this relative velocity. Please follow the diagram. Check the diagram. Here we have the first body moving with velocity v bar. The second body moving with velocity u bar. V bar is the velocity of the first body. U bar is the velocity of the second body. Both are in the moving condition. Here V bar is called the absolute velocity of the first body. V bar is called the absolute velocity of the first body. Dear students, in physics, in the lower classes in physics, you might have studied that velocity of the moving body, the rate of displacement of moving body is called velocity of moving body. When the body is in moving condition, we measure the velocity of that moving body with respect to earth surface. So please everyone listen this carefully. When the body is in moving condition, we measure the velocity of moving body with respect to earth surface. We assume the earth is in rest condition. With respect to the earth surface in the rest condition, we measure the velocity of body 60 km per hour, 50 km per hour or 5 meter per second. All are measured. All the velocities are measured with respect to earth surface. If we measure the velocity of a moving body with respect to earth surface, we call that velocity as absolute velocity of the moving body. So please listen this carefully. If the velocity of a moving body is measured with respect to earth surface as a reference, by taking the earth surface as a reference, if we measure the velocity of a moving body, that velocity is called absolute velocity. So in this diagram, V bar is called absolute velocity of the first body. U bar is called absolute velocity of the second body. So follow that carefully. V bar is called absolute velocity of first body. U bar is called absolute velocity of second body, because we measure those velocities V bar and U bar with respect to earth surface. Velocity is a vector quantity. Velocity has the magnitude, velocity has the direction, velocity obeys the vector law of addition. So the velocity is a vector quantity. That's why we consider the velocity of first body as V bar. velocity of second body as u bar. V bar is called absolute velocity of the first body. U bar is called absolute velocity of the second body. If the velocity of the first body V bar is greater than the velocity of the second body U bar, then the first body strikes the second body, that is here. If the velocity of the first body V bar absolute velocity is more than the absolute velocity U bar of the second body, the first body strikes the second body. When the first body strikes the second body, the first body strikes the second body with the relative velocity VR bar, not with velocity V bar. Here, the first body strikes the second body with the velocity VR bar, not with velocity V bar, because the second body is also in the moving condition. If the second body is in the rest condition, then the first body strikes the second body with velocity V bar. But here, the first body is in moving condition, second body is also in moving condition. So, the first body strikes the second body with the velocity VR bar. VR bar is called the relative velocity of the first body with respect to second body. So, in the diagram, first body is in moving condition. Second body is also in moving condition. Since the two bodies are in moving condition, the first body strikes the second body with the velocity VR bar called the relative velocity of the first body with respect to second body. VR bar is equal to V bar minus U bar. The relative velocity of the first body with respect to second body, VR bar is equal to the absolute velocity of the first body minus the absolute velocity of the second body. That is VR bar is equal to V bar minus U bar. Now, in the diagram, all the velocities are in the same direction. V bar is horizontal. U bar is horizontal. VR bar is also horizontal. If all the velocities are in the same direction, you can write this vector subtraction. This is called the vector subtraction. VR bar is equal to V bar minus U bar. If all the velocities are in the same direction, then the magnitude of this relative velocity VR. VR is the magnitude of the relative velocity VR bar. VR is equal to V minus U. V is the magnitude of the absolute velocity V bar. U is the magnitude of the absolute velocity U bar. So, if all the velocities are in the same direction, VR is equal to V minus U. So, please understand this. If the first body and also the second body, if both are in the moving condition, the first body strikes the second body with relative velocity, not with the absolute velocity. VR bar is the relative velocity of the first body with respect to second body. That VR bar is equal to V bar minus U bar. If all the velocities are in the same direction, then VR is equal to V minus U. So this is the concept of relative velocity. In this moving metal plate, just now we discussed the impact of water jet on the moving metal plate. In this moving metal plate condition, the water jet is in moving condition. The metal plate is also in moving condition. Since the water jet and metal plate both are in the moving condition, we must apply that relative velocity for all these cases. For all these cases, we must apply the relative velocity. That's why I explained that relative velocity basics here. The first body, water jet, moving condition. The second body, metal plate, moving condition. Since both are in moving condition, the water jet strikes the metal plate with relative velocity, not with this absolute velocity. The water jet strikes the metal plate with relative velocity. VR bar is the relative velocity of the water jet with respect to moving plate. That is V bar minus U bar. If all the velocities are in the same direction, VR is equal to V minus U. So with this, I am going to stop the today's class. Dear students, if anybody is having doubt in this discussion, in the today's class discussion, you please discuss with me. If you are not having the class, you please leave the class.